Good morning, everyone. Today we are diving into the critical engineering process of line sizing calculations. Our session will cover everything from the fundamental theory and industry criteria to practical heuristics and a demonstration of our internal pipe design tool. By the end of this presentation, you'll have a comprehensive understanding of how to optimize piping systems for both performance and cost. To begin, let's look at why line sizing is so vital. In a typical chemical plant, piping accounts for a massive 25% to 40% of the total capital investment. Furthermore, the power consumed by pumps is a significant utility cost, and this is directly dictated by the line size chosen. Therefore, economic optimization isn't just a technical task, it's a financial necessity for any design engineer. Different organizations follow specific criteria. A KBR, for instance, focuses on controlling operating conditions and economic factors. A key rule here is providing a control allowance, essentially reserving about 25% of variable friction losses for control purposes. For example, if your system has a 4-bar pressure drop available, you'd typically size the line to utilize about 3 bar under normal flow conditions. Alternatively, the NORSOK standards emphasize minimum life cycle cost. This approach is more holistic, looking at weight, energy, and maintenance over the entire life of the pipe. It also places heavy emphasis on physical constraints like noise, vibration, and material degradation. In many real-world scenarios, these technical constraints will actually override pure economic calculations. Beyond costs, we must monitor specific physical quantities. We look at velocity to prevent erosion, momentum to avoid water hammer, and the kinetic term to manage impact pressure and vibration. We also consider the rho times velocity cubed term for noise control, as well as head loss per unit length and the Mach number to ensure the system operates within safe physical limits. Now, let's get into the theory. For single-phase incompressible fluids, we rely on the Darcy formula. This is the gold standard for calculating head losses in both laminar and turbulent regimes. Whether you're working with volumetric flow or mass flow, the Darcy equation provides the mathematical foundation for our pressure drop calculations. A critical component of the Darcy formula is the friction factor, denoted as F. For laminar flow in circular pipes, we use Poiseuille's equation, which is straightforward. However, for turbulent flow, we transition to the Colebrook equation, which accounts for both the Reynolds number and the relative roughness of the pipe's internal surface. When dealing with compressible fluids like gases, the Darcy or Duckler formulas remain applicable as long as the head loss stays under 10% of the starting pressure. We often assume isothermal flow for convenience. It's also important to remember that the maximum fluid velocity is capped by the sonic velocity, the speed of sound in that specific fluid, which occurs when the final absolute pressure drops to roughly half of the initial pressure. Two-phase flow, involving both gas and liquid, is significantly more complex. The flow regime depends heavily on orientation and roughness. To calculate head loss, we must identify the flow pattern and the liquid holdup. We use specific maps for this, Baker's or GM maps for horizontal flow and Aziz's map for vertical flow, to ensure our correlations match the physical reality of the pipe. This visual represents the Baker's correlation from 1954, updated in 1969. It maps out different flow patterns, such as slug, plug, or annular flow, based on the mass velocities of the gas and liquid phases. Understanding where your process sits on this map is crucial for choosing the correct pressure drop correlation. In mixed-phase lines, we must also check for erosion velocity. We use an empirical constant C to set these limits. For continuous service, we typically cap C at 100, while for intermittent service, we can allow it to go up to 125. This prevents the high-velocity fluid from physically wearing away the pipe walls over time. To summarize our formulas, for single-phase gas and liquid, we use Darcy with Colebrook or Poiseuille friction factors. For mixed-phase, horizontal and vertical pipes follow the Duckler method, as recommended by AGA and Snam-Progetti criteria. For vertical lines specifically, we apply the Flanagan correlation to account for elevation changes and hydrostatic head. Moving on to physical pipe specifications, let's discuss schedule numbers. While pipes used to be called standard or extra strong, We now use schedule numbers to identify wall thickness relative to nominal bore. This number is a ratio of internal pressure to allowable working stress. Generally, Schedule 40 is our go-to for low pressure, while Schedule 80 is reserved for high pressure or high temperature applications. It's important to clarify nominal size. For pipes up to 12 inches, the nominal size is roughly the inside diameter. Above 12 inches, it actually matches the outside diameter. We also have to consider roughness, those tiny geometric irregularities inside the pipe. Roughness affects the velocity distribution and is a major factor in determining whether the flow is effectively smooth or fully turbulent. In daily practice, we use heuristics to speed up the design process. For example, for pump discharge, a good rule of thumb is a velocity of 5 plus d over 3 feet per second. For vertical gravity lines, we aim for a Froude number below 0.31. This prevents gas entrainment and ensures we don't deal with unwanted pulsations or glugging in the line. When working with carbon steel and corrosion inhibitors, we limit velocity based on wall shear stress, typically 40 newtons per square meter. Additionally, to ensure a pipe is sealed in horizontal flow, we can use the Q equals 10.2 times d to the power of 2.5 formula to calculate the minimum liquid flow rate required. On this slide, you can see a reference table for nominal diameters, external diameters, and wall thicknesses. This is the data we feed into our calculations to ensure we are using the actual internal diameter rather than just a nominal approximation. Let's look at specific criteria for the gas phase. These parameters ensure that we maintain enough pressure for downstream equipment while keeping noise and vibration within acceptable limits for the plant environment. Continuing with gas phase criteria, we pay close attention to velocity limits. High velocities in gas lines can lead to significant acoustic energy, which can cause fatigue in piping components if not properly managed. For the liquid phase, the focus shifts toward preventing cavitation at the suction side and managing the pressure drop at the discharge side to optimize the pump's power consumption. Mixed phase criteria are perhaps the most stringent. Because these lines carry both gas and liquid, the risk of slugging and erosion is much higher, requiring a more conservative approach to sizing compared to single-phase lines. In this section, we provide a summarized view of the various sizing criteria across different service types, serving as a quick reference guide for the design team during the initial phases of a project. This table provides recommended velocities and pressure drops specifically for carbon steel vapor lines. You'll notice that as the pressure level increases, the allowable pressure drop per kilometer also increases. For example, lines above 35 kilograms per square centimeter can handle up to 4.4 kilograms per square centimeter of drop per kilometer, whereas vacuum lines are limited to just 0.22. We also have specific guidelines for specialized services. Whether it's utility steam or hazardous process chemicals, the sizing must reflect the unique risks and physical properties associated with those fluids. As mentioned earlier, internal roughness values vary by material. This slide lists the absolute roughness values for materials ranging from drawn tubing to heavily corroded cast iron, which is essential for accurate friction factor calculations. Finally, when the pressure drop exceeds 10% in gas or mixed-phase lines, the Darcy equation's assumptions begin to fail. In these cases, we must use an iterative approach, calculating the change in density and velocity along segments of the pipe to ensure the final design is both safe and accurate. Thank you for your attention, and we can now move to the software demonstration.